discuss some ways that you can finish that laboratory. So let's take a look. Today we're reviewing for Monday's test over thermodynamics. So that's pretty quick. If you don't have a copy of that review, you can click right here. It's not many questions, but there are several on there. And then if we take a look at next week, basically it will be the thermodynamics test on Monday. So there will be no in-class Zoom. It's always fun whenever people come into the Zoom and I'm like, yeah, you can go do this, or you can ask me questions or whatever. And then Tuesday and the rest of the week, I'm actually just going to copy paste this for the rest of the days of that week. As you can see, it's not done completely, but both the 9 weeks review, which is the first half of the final exam review, and then the final exam review part 2 have been videotaped and recorded. So you can go through those with me. And then next week, basically will be question and answers in the Zoom. Maybe a 5 to 10 minute thing real quick at the beginning to go over in more depth some of the more difficult topics each day. And then, so after 10 minutes, then I would let you just go off and work on that review after that. That would be Tuesday, Wednesday, Thursday, and Friday of next week. And this is period 2. So your final exam will be the following Monday, 12th, 13th. That would be December 14th, I believe. So let's go ahead and take a look then at the thermochemistry review. So key things about this is, hopefully this is visible. Key things about this is that you need to know, like, for example, the units for everything. For mass, we would have grams. This C or S is the specific heat capacity. Both letters have been used either for capacity or S for specific heat, and that is joules per gram degrees Celsius. And then your temperature obviously would be in degrees Celsius. And then for your, excuse me, amount of heat, that would be joules, calories, kilojoules. All of these are valid for the heat. Now, if your specific heat capacity is in joules per gram degrees Celsius, obviously, then that's going to be in joules whenever everything cancels out here. Zoom in a little bit on that. If heat is absorbed in the reaction, then it is called endothermic. For example, if you are inside and you have an electric blanket, or you're sitting next to a fire, your body would be gaining energy from that fire, and that would be warming you. If you're touching something and it feels warm, then to your body, that is an endothermic change. If you're touching something and it feels cold, that would be exothermic. Exothermic is when heat is released. Now, what is heat? Heat is known as the basically what we would call the movement of energy from something of higher temperature, or the transfer of energy from something that is of higher temperature to something that is of lower temperature. So keep that in mind. Heat itself is the transfer of energy. When we look at something, we talk about the kinetic energy that it has. That is not heat. The kinetic energy that something has is would be considered the temperature of it. So the actual heat is the transfer of energy from something that is of higher temperature to something that is lower temperature. From higher temperature, let's say object, to something that is lower temperature. Sniffles, cough. Oh, I hope I'm healthy. All right, so if we take a look, let me pose this question. Let's say I have a cup of coffee just like this right here. This coffee is probably around 40 degrees Celsius. And let's say we have an iceberg. Which one would actually have more heat in it? An iceberg or that cup of coffee? It's just kind of a trick question because how many of you actually know the size of like an iceberg? Whenever they say the tip of the iceberg, the majority of the mass of the iceberg is actually underwater. Does anybody want to put themselves out there? No. The iceberg would actually contain more heat than a cup of coffee. Imagine if we take, for example, a pail of water at, let's say, 100 degrees Celsius, and we take a swimming pool at, let's say, 27 degrees Celsius. Imagine now, instead of if we were dealing with, let's just say 20 degrees Celsius. Imagine now if we were dealing with a bucket of water at 100 degrees Celsius. Let's change that to a bucket filled with $100 bills. And we change the swimming pool at 20 degrees Celsius. We change that to a swimming pool filled with $20 bills. Which one would you rather have in your bank account? A bucket filled with $100 bills or a swimming pool filled with $20 bills? Now, if you were smart, even though the nomination of the bill is less in the swimming pool, there's going to be a lot more of those bills. So that would mean that you would hopefully want the swimming pool. Heat can be looked at the same way. If we look at the objects in there, the 20 degrees water, there's more heat because there's more mass of water in the swimming pool than there is in the bucket at 100 degrees water, 100 degrees Celsius. The specific heat capacity is known as the amount of energy required to change 1 gram of the substance 1 degree Celsius. If we look at that, then that should be good. There is no temperature change during a phase change. So let's do question 4 first. It says describe a graph or draw a graph with temperature on the y-axis. And on the x-axis, labeling the phase and delta H on the x-axis. That's the amount of heat. So if we take a look, we start here. And let's go ahead and put -10. At -10 degrees up to 0 degrees, that's going to be a solid. That's going to be ice. Solid. Here, that is melting or freezing. Notice again, there is no phase change. I'm sorry, there's no temperature change there. The temperature remains at 0 degrees Celsius. Here you would have solid and liquid on that line. Here we see a change again in temperature. So this would all be liquid. And then somewhere around 100 degrees, we have another plateau. This would be what we call vaporization or condensation. This would be where you would have liquid and gas. And then after that is vaporized, you would see an increase in temperature again. And that is where you just have the gas. Again, notice these flat lines mean that there is no change in temperature. Now, we probably know solid, liquid, gas, and how ice melts and then turns to liquid and then vaporizes and turns to gas. There is another process that can occur where a solid goes directly to a gas, and this is known as sublimation. And where a gas goes directly to a solid, this is known as deposition. Like basically you are depositing particles. So if we take a look, melting and vaporizing, the ones written on top, and sublimation, those are all endothermic. Melting, vaporizing, and sublimation. Exothermic processes is when we lose heat. So if something is freezing, condensing, condensation, or depositing or deposition, those are exothermic. They're losing energy. So that's a pretty good review of that, whether it's endothermic or exothermic, as well as our devices here, our changes in state. And keep in mind that temperature is the amount of kinetic energy versus heat is the transfer of energy. Temperature is measured with a thermometer. Change in heat is measured with a calorimeter. The calorimeter was that metallic and styrofoam and plastic device that I had with the lid. Basically what that does is that separates the environment to the system so that there is no heat lost to the environment. So keep in mind the instrument we would use to measure heat would be the calorimeter. The last part of this unit is calculating changes in heat. So we take a look. How many joules would be required to raise the temperature of 387 grams of water from 27.05 to 145.4? If the specific heat capacity of water is this, you'll want to keep that heat capacity. You'll probably want to write that down before you take the test. Is this process endothermic or exothermic? Well, it says that it's raising the temperature, so that would be endothermic. We are gaining energy. Let's find the delta T. 27.05 up. 145.4 minus 27.05.
The answer is 118.35.
118.35 degrees Celsius. To find the amount of heat, we take the mass times the specific heat capacity times that delta T. So the mass of this is 387 grams. The specific heat capacity is 4.184 joules per grams degrees Celsius. And the temperature change is 118.35 degrees Celsius. 387 times 4.184 times 118.35.
It's 191,633.2668.
We're going to round that to 3 significant digits. So that is 192,000 joules. So that's joules. If we wanted to, we could change that to kilojoules. If it asks for how many kilojoules, we would just divide this by 1,000. Next, it says how much heat must be added to a 75 gram of iron block to increase the temperature from 25 to its melting temperature of 1535 if the specific heat capacity is 0.451. Is the process endo or exothermic? We are raising the temperature again, so it is endothermic. 1535 minus 25.
It's 1,510.
So there is our change in temperature. Again, we're going to take the ms delta T. The mass of this block is 75 grams. I was going to write iron, but I don't need to. The specific heat capacity, since this is a different type of material, its specific heat capacity is going to be different. This is metal, so it's going to be lower than that of water. Water actually has what's considered to be a pretty high heat capacity. That's why water can be used to basically take heat away. Water and glycol are used to take heat away from like your car engine, or water is used to cool down things like during a fire. If you add water to it, like the surroundings and stuff like that, that water will absorb the energy versus letting whatever it is that's on fire, catching fire and burning. Another key thing is, as remember, our specific heat capacity allows us to cancel out these units, leaving us with joules. 75 times 0.451 times 1510.
That would be 51,075.75.
Three significant digits, so 51,100 joules. The specific heat capacity of ice is 1.95 joules per grams degrees Celsius. Notice that water and ice are different. They have it different from their state of matter. How much heat in joules is required to heat a 35.5 gram ice cube from -23 to -1? So that's a change of 22 degrees Celsius. And again, we're going to take ms delta T. The mass of this cube of ice is 35.5 grams. The temperature, the specific heat capacity is 1.95 joules per grams degrees Celsius. And the change in temperature is 22 degrees Celsius. 35.5 times 1.95 times 22.
It's 1,522.95.
Three significant digits, so 1,520 joules. Now, if we take a look, we know the formula is Q equals ms delta T. So for your laboratory, you knew the mass of the water in the calorimeter cup. The specific heat of water is 4.184 joules per grams degrees Celsius. You know the change in temperature of the water, I believe it was something like 22 or 20 or something like that. And then whenever I put the metal in there, it went up to 22 or 24. So that is the T of F minus the T of I. Again, that was an endothermic process. The water in the cup absorbed energy from the piece of metal. So with these three things, you should be able to find the heat the water absorbed. So now you have a Q. And these are those last two questions where you're trying to solve the things. So now you have the heat the water absorbed. That heat the water absorbed is equal to the heat the metal lost. So now we have Q, M, S, and delta T. What we don't know is the specific heat capacity of the metal. So what you do to find that is you rearrange this formula to solve for S. We divide both sides by M delta T. You know the Q because it's the amount of heat that was absorbed by the water. You know the mass of the metal, and the metal's change in temperature was from the boiling water, 99 point something, and it went down to the same temperature final of the water, because as those two things sat by each other, and their molecules were touching, or their atoms were touching the molecules of water, they equalized at the same temperature. So by plugging in these things, you would be able to find the S. So now you have that S, and that is the experimental S. Well, aluminum, it's the S of aluminum, the theoretical, is equal to 0.900 joules per grams degrees Celsius. To find the what we call the experimental air, you take the theoretical minus the experimental, and you divide that by the theoretical. This is an absolute value up here, and then you multiply that by 100 to equal your error by percent. So those of you that did not complete the laboratory and turn that in, you want to make sure that you go through and do these problems with that information from the laboratory. That's all I've got really for the review for the quiz. There is no Zoom on Monday. If you need help, you can watch this video, or you can watch the videos from earlier in the week to do those heat problems from the thermodynamics packet. Make sure you have those notes looked over before taking the test. It's actually more of a quiz. I think it comes out to be, let me check. Looks like it is a test. It is worth 100 points. So there are enough questions on there to equal 100 points. So I did make a, oh, I'm sorry, I got the wrong test open. Okay, 1 second. Thermo quiz, there we go. 70 points. Take a quick look, make sure. Boom, 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 boom. Yeah. Covered that, covered that. Remember, 1 calorie is the amount they get to raise 1 gram of water 1 degree Celsius, and that 1 calorie is equal to 4.184 joules. Yep, quiz is ready to go. If you have questions, by all means, stick around. If you need to make up something because of absences or other reasons, stick around. Make sure that I understand that, because I can't understand what you don't tell me, right? It's like that song, Lean on Me. I cannot help you if you don't tell me what you need. Have a great weekend. Happy Friday. Take care of yourself. Take care of others. And get out of here.
Have a good day.
Thank you, Amani. You too.